Okay, very good. So thanks, Ivan. Thank you very much. In principle, this talk is essentially independent of last week's talk, but in some sense it continues on the same theme because I'm still going to be talking about the interaction between natural selection and spatial structure. But whereas last week the spatial structure was just that there was a population which was already at some sort of constant intensity right across space, now my population is going to be expanding, and we're going to look at what happens at the front of that wave of expansion. And just like last week, I think it's wise to thank one's collaborators early on. So I say collaborator, actually these people did all the work. Most of what I talk about, possibly all of what I talk about, depending on how time goes, is work of Felix, who Amaury already told you about. So Felix is a student of Amaury and Emmanuel Scherzer, and they very kindly lent him to me for a few months before he started his doctorate. And he came to Oxford and did what I find very interesting work. So that's mostly what I'll talk about. And then if time permits, I want to advertise what I think is some rather remarkable new work of Sarah Pennington, who's now in the University of Bath. Okay, so as before, let's start without any space and just see if we can think a little bit about what our intuition, where our intuition would take us from a non-spatial model. So last week we talked about the Wright-Fisher model, and this time I want to look about the Wright-Fisher model with selection, which we discussed very briefly. So suppose that my population is split into two types, and little a and capital A, and one of those types is going to be slightly fitter than the other. So the capital A individuals are going to be more successful at reproducing than the little a individuals. And how's that going to work? Well, my population will evolve in discrete generations. It's fixed size n, it evolves in discrete generations. And during reproduction, each individual produces an effectively infinite number of gametes. So think of those as potential offspring. But a type little a individual produces 1 minus s times as many gametes as a type capital A. And that's where natural selection comes in. And then to form the offspring, I just sample n individuals uniformly at random from that pool of gametes. And that's my offspring. So another way to say that is actually that the n offspring sample their parent independently at random from the previous generation, except that they do it in a weighted way. So a little a individual has a weight 1 minus s times that of a capital A individual. And if the proportion of little a alleles in the parental population is p, then the probability that an offspring is going to be type little a will just be, well, to a good approximation, p minus s times p1 minus p, where s is this small selective disadvantage in this case to the little a alleles. And just as last week, if I'm looking at a large population, I might as well approximate those dynamics by a stochastic differential equation. And now we see the Wright-Fisher diffusion that we saw before. So that's this, this stochastic term here. This corresponds to the genetic drift. But because of natural selection, there's an extra term, which is this downwards drift in the mathematical sense to the frequency of little a alleles. Now, what you might imagine happening is that I've got a population which is constituted entirely of capital A individuals of the fitter type. And then a mutation arises to this less fit type, little a, so a deleterious mutation arises, and it arises in a single individual. And one might ask, well, what's the probability that that deleterious mutation will actually eventually be fixed in the population, which just means that everybody in the population will carry it. And if we're working with one-dimensional diffusions, what's rather nice is that we can calculate things very easily using the theory of speed and scale. And we find that the probability that that deleterious mutation fixes is roughly e to the minus twice the effective population size times the selection coefficient. So what that says is that the bigger the population, the more effective natural selection is at eradicating these deleterious alleles. Or if you prefer the other way around, the smaller the population, the more likely genetic drift, so the stochastic term is, to allow a deleterious mutation to fix. And from the perspective of what we're going to be talking about today, that suggests that natural selection is going to be less effective at the front of an expanding population where the population size is smaller. And so if a deleterious mutation arises at the front of the population, it might not be eradicated as easily as it would be in the bulk of the population where the population size is bigger. And of course, there are also other reasons why you might want to be living near the front. If you're a deleterious mutation arising in an individual, it might be that the advantage is that the individual carrying you has from living on the front are more than enough to outweigh the disadvantages that you bring them as a deleterious mutation. So there might be more light or more nutrients or more space or whatever. Okay, and you must admire that the artwork, which was not done by a small child, but it was done by someone as good as a small child wishing to play with her new computer. Okay, so what that suggests is that it may be possible for deleterious mutations to accumulate at the front of an expanding population. So I think I flipped 2 slides at once, arguably. No, I didn't. Okay. So what we want to investigate is it possible that deleterious mutations can accumulate at the front of an expanding population? And in order to investigate that mathematically, I first of all want to talk about a model for the accumulation of deleterious mutations when there's no space. So our assumptions are going to be, as usual, ones which really caricature the biology in a horrendous way, but they will capture the key features which will tell us how the population might evolve. So we're going to take an asexual population, which is what we've done all along. It makes life much easier, constant size. And we're going to suppose that individuals accumulate mutations and that all mutations are deleterious. In fact, in reality, most mutations are deleterious, and most of them have a small deleterious effect. For simplicity, and because it'll be mathematically very elegant, we're going to suppose that the deleterious effect of each mutation is the same. So if I'm an individual who's accumulated k deleterious mutations, then my relative fitness will be 1 minus s to the k. It wouldn't be a very different picture if I took different effects for different mutations, but as I say, the mathematics this way will be quite elegant. Okay, and as a notation, I'm going to write xk of t for the proportion of individuals at time t that carry exactly k deleterious mutations. Okay, and here's a model due to Hay. This is a simple analog of the Wright-Fisher model, or a simple variant of the Wright-Fisher model. So the population will evolve in discrete generations. Each offspring independently is going to choose its parent from the previous generation in a weighted way. But now, instead of just having the 2 types that we had in our Wright-Fisher with selection with the relative weights 1 minus s to 1, we're now going to have a different type for each of the different numbers of mutations that an individual might carry. All mutations are going to be passed from parent to offspring. That was an assumption we also made in our Wright-Fisher model with selection. But now we're also going to allow additional mutations to occur. So each offspring is going to accumulate a Poisson number of new mutations. So in addition to inheriting all the mutations from its parent, it's going to also accumulate an additional Poisson number of mutations. Okay, so let's make that more mathematical. So if in generation T, my frequency profile, by which I mean the vector which tells me the proportion of the population that carry exactly k mutations for each k, is given by that little x. So that just says that the number of individuals in generation T that carry k mutations is n xk of t. Then the number of mutations that an offspring will inherit from a parent is k with probability 1 minus s to the k times xk of t, because I'm picking my parent in a weighted way, and the relative weight of a parent that carries k mutations is 1 minus s to the k, and then divided by this normalizing factor, which just makes everything add up to 1. Okay. So for each individual in the offspring population, that probability tells me the probability they inherit exactly k mutations from their parent. And then in addition to that, each of them independently inherits or accumulates a Poisson number of new mutations. So if I write k1 up to kn for independent copies of the random variable h, which has this probability mass function, which tells me the inherited mutations, plus j, which are these Poisson new random variables, then this k1 to kn will give me the number of mutations carried by individuals labeled 1 through n in the offspring population. And so I'm going to write xk of t plus 1 for just 1 over n times the number of indices I for which ki equals k, and that's the proportion of individuals among the offspring that carry exactly k mutations. So note this 2-step transition. I sample a parent, I inherit all of their mutations, and then I add on a Poisson number more mutations, and I do that independently for each of the offspring. Okay. Well, now something really neat can happen. Suppose that in the parental generation, that frequency vector is given by this very special form, which is just Poisson weights. So the number of individual, or the proportion of individuals that carry exactly k mutations is theta to the k e to the minus theta over k factorial. Then the probability that an offspring inherits exactly k mutations is again going to be a Poisson random variable. So just substituting into this formula, which says it's 1 minus s to the k xk of t divided by the normalizing factor to make everything sum up to 1, which in this case will be e to the minus theta s, then I obtain that the probability that h is k is a Poisson, is the Poisson density or Poisson mass function corresponding to parameter theta times 1 minus s. Okay. And then I'm going to add on to that another Poisson number of mutations. And so h plus j, the number of mutations each individual carries, is actually going to be a Poisson random variable with parameter 1 minus s times theta plus mu. And of course, as n tends to infinity, if I'm sampling an infinite number of individuals from this pool, the proportion that carry exactly k mutations will be given precisely by the probability mass function for k mutations. And that's that's the Poisson mass function for k mutations when the Poisson has parameter 1 minus s times theta plus mu. And now I can do something even smarter. I mean, I'm always of the view that we only do probability theory because Poisson random variables are so nice. And in this case, they're particularly nice because if I now choose my theta to be mu over s, then I discover that 1 minus s times theta plus mu is theta. So I end up with a fixed profile for the proportion of my population carrying each of the different numbers of mutations. So if I'm looking at an infinite population limit, then I get this Poisson fixed point. And the proportion of the population that are carrying exactly k mutations is just a Poisson random variable with parameter theta, where theta is mu over s. And actually, if I look at this infinite limit where I just always sample an infinite number of individuals in each generation, I get a deterministic dynamical system for the proportion of individuals carrying each of the different possible frequencies. And it converges very rapidly as long as in the initial population, some individuals carry no mutations. This will in fact converge to this Poisson profile. Okay. So that's very nice, but of course, and this is a form of mutation selection balance because although every individual accumulates mutations, their offspring are more likely to be picked from individuals carrying fewer mutations, and that gives you a balance between selection and mutation. But of course, populations aren't infinite, they're finite. And in a finite population, just purely by chance, at some generation, I'm going to sample entirely individuals that have inherited no mutations and moreover do not accumulate any new mutations. And so in the offspring population, I don't see any individuals that don't carry any mutations. And once that happens, I can never get back to a population in this model in which individuals carry no mutations, because everyone is going to inherit at least one mutation from their parents, because the parents all have at least one mutation. I can then continue the process for a bit longer, and after another finite random time, I will lose the next best class. So suppose that after the first this first time t0, when I lost the class with no mutations, suppose that everybody had, there were some individuals with just one mutation. Well, after another finite random time, I'll no longer have individuals that have one mutation. I'll only have individuals that have at least two mutations and so on. And this is a model called Muller's ratchet. And the idea is the ratchet clicks, and when the ratchet clicks, I can't go backwards. So that's what this picture is meant to represent. And the population becomes inexorably less fit. Okay, and this model is sometimes used as an explanation for why we might have the evolution of sex, because if we have chromosomes mixing between parents, then it's possible to recover populations in which individuals in which there are no mutations. Okay, so now let's think about what happens to a population expanding its range, having in mind this idea of the Muller's ratchet. So mutations arising at the front of a population that's expanding its range can reach high frequency even if they don't confer a selective advantage. And the reason for that is just because there might be advantages of living at the front that we saw in our previous cartoon of there being more space or more nutrition or more light or whatever it might be. So here's a cartoon of how that might work. And these pictures were produced by Felix, which is why they look so much more professional than mine. So this is meant to represent a single green mutation arising in the front of the expanding population. As the population expands, the green mutation produces a lot of offspring because there's a lot of space at the front. It's not competing with too many other individuals, and those offspring disperse. And over time, one can imagine that the green population might completely fill out the front. And then as the front expands, everybody in the front of the population is carrying at least one of these mutations. And that mutation didn't need to confer a selective advantage. It just needed to exploit the advantage of being at the front of this expanding wave. And this phenomenon is called gene surfing. I said green surfing, as it is in our picture, gene surfing. And if it happens with deleterious mutations, so if that green mutation was actually deleterious to the population, and if perhaps we then see another mutation arising on top of that green mutation, which makes it even less fit, but because of the extra fitness of the extra advantage of being born at the front, that's also allowed to expand and take over the front, then we get an accumulation of deleterious surfers, and that's referred to as expansion load. Now, expansion load relies on the idea that it's good to live at the front of an expanding population. But it may not always be good to live at the front of an expanding population. Sometimes there are disadvantages of living on the edge. You might be finding it difficult to find a mate. It might be that you're more exposed to predators, or you might just be downright cold. So this was not by the same artist. This is a sketch sent to my daughter because she had COVID and had nothing better to do. So this is a penguins on the edge of a colony feeling the cold. So what Felix wanted to explore was what's the interaction between how good life is on the edge and this expansion load. And to explore this, we want to understand the interaction between natural selection and what's called an allele effect in ecology. So the allele effect says that the maximum per capita growth rate may be achieved at an intermediate population density. You don't want to be where it's densest because there's too much competition for resource, but you may not want to be living life on the edge where you might be exposed to predators or the cold, or you might find it difficult to find a mate or whatever. Okay. And loosely speaking, if there's no allele effect, that's the kind of picture we had in our first cartoon, and the expansion of the population is determined entirely by what's happening in the front, then we're going to have something called a pooled wave. And if there's a strong allele effect, which means that it's actually disadvantageous to be right at the front, but advantageous to be at some intermediate density, then that gives rise to what's called a pushed wave. And the cartoon now changes slightly. So in the bottom picture, we have our pulled wave, where initially, and what Felix has done now is he's drawn stripes to indicate where people originate in our model, or where individuals originate. So right at the front, he's labeled them in a dark color, and then we have green, and then we have yellow. And then he said, well, if I've got a wave of expansion, never mind additional mutations, I just look at those different types. I've just stained the individuals in my population with these colors, and I let the population expand. Where are the descendants of those dark colored individuals? And in a pulled wave, winners beget winners. So the descendants of the dark individuals will start to fill out the wavefront because they grow more successfully and they spread out, and they are going to populate the wavefront. In a pushed wave, which is what the top cartoon illustrates, the maximum growth rate is among these green individuals. They produce more offspring than either the dark individuals or the yellow individuals. And moreover, they're going to spread out. And gradually over time, we might expect that those green individuals start to invade the wavefront. Okay, well, this was just a cartoon which was drawn to illustrate what might be happening. Here for a deterministic model is a numerical simulation of what happens. So this is from Rock et al. It appeared in PNAS in 2012. Now, the differential equation that they're looking at for the whole population is this one here. It's this reaction diffusion equation. And if the blue term isn't there, we've got the famous Fisher-KPP equation, which is the classical model for a pulled wave, for an expansion which is determined by what's happening in the front. And the picture that we see on the top right is for that pulled wave. And let me explain how they arrive at that picture. So they do what Felix did in his cartoons. They stain the population according to where it is at time 0. And they actually rewrite this equation in terms of as u times, and then instead of 1 minus u, I would write some function of u, and I'll preserve that u. But the first u, this u here, and this u here, and this u here, I'll think of as composed of lots of separate equations, which I might call V1 for the gray, V2 for whatever color comes next, V3, V4, V5 when I get to the cyan, and so on. And I express u as the sum of all of those VIs. And the equation for the VIs, which I should have put on the slide, and I apologize for not doing so, would be that d by dt of VI would be the Laplacian applied to VI plus VI times 1 minus u. So the rate at which VI can expand is still controlled by the entire population, but I've broken the population down so that I can see where individuals were descended from. And what we see in this Fisher KPP picture, which is the top right-hand picture here, is exactly what Felix's cartoon predicted, that we see that the front is taken over by individuals that were in the front at time 0. But then Rock et al. Add to this 1 minus u, or multiply this 1 minus u, by an additional term of the form u minus rho, where rho is a parameter between 0 and a half. So by taking rho less than a half, we guarantee that we're going to have a wave of expansion to the right. And by taking rho to be bigger than 0, we see that the growth rate right at the front, where the population is smallest, is negative. And this is called a strong Allee effect. It's strong Allee effect because it's actually disadvantageous to be at the front, and the optimal growth rate is somewhere in the middle. There is also something called a weak Allee effect, where it's still advantageous to be at the front, but not as advantageous as it is to be somewhere else. And we're not going to consider that. We're just going to look at the strong Allee effect. And in the bottom pictures, what Rock et al. Have done, they've done exactly what we did for the Fisher KPP equation, except that we get VK for the kth type multiplied by 1 minus u, u minus rho. So still controlled by this, this whole u term, the whole population, but where we've essentially stained individuals with a dye which says where their ancestors were at a time in the past. And you see that Felix's cartoon again was correct, that we start to see this horizontal striping developing. So with an Allee effect, we're seeing that individuals that were in the bulk start to invade the front as time evolves. Okay, and that's what we wanted to investigate in the context of natural selection interacting with genetic drift. So we wanted a noisy model that would incorporate this Allee effect. And as usual, we want to start with an individual-based model. And the individual-based model is going to look a bit horrible, but it's not really. It's just the notation gets a bit difficult. So we're going to take a population that is subdivided into demes. So it's in contrast to last week. I'm not going to do anything fancy with spatial lambda Fleming-Vio models. I'm going to suppose my population is subdivided. And I'm always going to denote the spatial subdivision by I. So I will always be denoting where I am in space. And K will always tell me the number of mutations. So that would be my notation throughout. And little nik is telling me the number of individuals at location I that carry exactly K mutations. And the total population size in DMI is going to be this capital Ni. Okay? And that's going to be, I'm going to be using that quantity to model competition for resources. And I'm just going to have a birth-death process. So an individual in DMI that carries K mutations is going to give birth to a new individual at a rate which will depend on the number of mutations that it carries, K, and it will depend on the total population size in the deme. So it's depending on that competition for resources and on the relative fitness of that individual, which is measured by the number of these deleterious mutations that it carries. Each individual in DMI is going to die at rate delta of Ni, and that's going to just depend on the total population size there. And in addition, individuals are going to migrate to left or right with equal probability at rate m. So I've just got nearest neighbor random walk. So in contrast to last week, we've got, and in contrast to our Wright-Fisher models of earlier in the lecture, we've got overlapping generations. Mathematically, this is simpler. The qualitative effect will be the same. Okay. And what form are we going to take for these lambdas? Well, let's suppose for a moment that there's this term here, which looks like b ni over n plus 1. Let's just take b to be 0 for a moment. If b was 0, then this would say that individuals give birth at a rate proportional to the number of mutations that they carry. That's 1 minus s to the k. And they die at a rate proportional to the local population size, which I've scaled by n. And this really is, it corresponds to a logistic growth. If I ignored mutation, this would correspond to a kind of logistic control of the population size where the carrying capacity was capital N. So I give birth faster than I die as soon as Ni is bigger than, sorry, other way, yes. I give birth faster than I die, so I tend to grow, provided Ni is less than N, but I die faster than I give birth as soon as Ni is bigger than N. Okay? But now we've got this additional term corresponding to mutations. And then on the next slide, we'll talk a little bit about this term involving B, which is meant to be a cooperation term. In addition to those births and deaths, I'm also going to suppose that with a certain probability, when an offspring is born, it has one more mutation than the parent. Okay. So let's talk about the role of B. So that's this, here's my birth rate, and here's my death rate. And in both cases, I've multiplied by this term, which I'm going to think of as cooperation. In a birth-death model, this is really just accelerating the rates of births and deaths. But one can mimic this in a Wright-Fisher model by having Poisson numbers of births and deaths with particular parameters. So it isn't really saying that generation time changes, but it's one way to think about it. So if B is 0, as we've just said, this is a stochastic version of the usual logistic growth with a carrying capacity. But if B is non-zero, the maximum growth rate might be at an intermediate population size. So in fact, if you can work it out, and this quantity, which you said, what's the maximum growth rate if I carry no mutations? Well, it's maximized at this value of the local population size. Obviously, if B is less than or equal to 1, that's just 0. So that's no Lie effect. That just says I'm still best off being right out in the front. But if B is bigger than 1, the maximum of that growth rate, of that intrinsic growth rate of my population, is at an intermediate population size. And the bigger B is, the more we see this Lie effect, the more this cooperative effect kicks in, and I get kicked towards the maximum growth rate being closer and closer to n over 2, to half the possible population size in my D. Okay, now discrete models are always a pain. So in order to make things a bit neater, I'm going to pass to a large population density limit. I'm not going to scale the reproduction rates, so they're still going to be happening at a finite rate. So this really will be a way of interpolating. What I'm basically trying to do is interpolate that discrete individual model to get something that's mathematically more tractable. But it's not really changing the qualitative behavior of the model at all. So I would rather be working in continuous space. Anyone who knows me knows I don't like discrete space. So let's work in continuous space. And to do that, I'm just going to apply diffusive rescaling so that the spatial motion of individuals, instead of being simple random walk, is going to be Brownian motion. Okay. And I'm now also going to scale the population density n. So I'm going to let the maximum population density be very, very big, but I'm going to count the number of individuals relative to that large unit of population density. So that means I'm going to rescale the population size in the ith deme. So remember, this will be the number of individuals in deme I carrying K mutations. I'm going to measure that in units of size n, and I'm going to call this scale property UK. Excuse me, it's a scaled quantity. And if I let n tend to infinity, and I start from enough individuals so I get something non-trivial, then in the limit, I would expect that I would arrive at a system of partial differential equations. And what would they look like? Well, here's my Brownian motion, this Laplacian term. This BU plus 1 is just the cooperation that we saw, mimicking the Lie effect. 1 minus s to the k, that's the relative fitness of individuals carrying K mutations. So UK, remember, is individuals carrying K mutations. And now this is a function along the whole of the reals. 1 minus u, because actually only a proportion 1 minus mu of them are not going to inherit an additional mutation, acquire an additional mutation. This minus u, this is the death rate. This is because I die at a rate proportional to the local population size. And then this growth of individuals is because individuals that carried K minus 1 mutations may acquire an additional mutation during reproduction, and that will result in an increase of the number of individuals carrying K mutations, and that's going to happen at a rate proportional to the fitness. So 1 minus s to the k minus 1 of those parents, the number of parents carrying k-1 mutations and the probability that an additional mutation lands on an offspring. Okay, so we recognize all the terms in that system of equations as having something to do with the model we first thought of. Okay, and now we're really interested, remember selection is always small, mutation tends to be small, and so we're interested in weak selection and weak mutation. And so all I've done now is I've replaced 1 minus s to the k by 1 minus ks, and I've thrown away terms that are multiples, so s times mu or order s squared, and they've all just disappeared. And then my system takes this rather easier form, so I just get this simple expression for my nonlinearity. Okay, that's all I've done. I haven't done anything fancy. Okay. Now, notice first that there are lots of solutions to this equation that we can find right away. So if my initial condition didn't depend on space at all, so it was independent of x, then so is the solution to that system of equations at all time. And we've already looked at solutions to that system of equations, at least in the case when k0 is 0. So k0, it's k0 is 0. So in which initially there are some individuals that carry no mutations, because that was what gave rise to our Poisson weights in our original model. And in fact, if we solve that dynamical system corresponding to the Muller-Ratchet, but with an infinite population size, starting from an initial condition in which everybody carries at least k0 mutations, then we arrive at this stationary state, UK star, which is again a Poisson system, but with a different weight. Okay. So we know lots and lots of solutions to this system if we're prepared to have a population that is constant in space. But of course, we're really interested in expanding populations. And what's interesting is to go the other way. So this said, if I hold the, if I start from something which is stationary in space, I remain stationary in space. I can also go the other way. If I start from something which everywhere in space I have a function which might vary with time, but I have a population which is Poisson, so that the distribution of different numbers of mutations at each point in space is Poisson, then that will be preserved with time. So if I'm homogeneous in space, that's preserved with time. If I'm Poisson in terms of numbers of mutations, that's preserved in time, where this theta is this magic mu over s. And in that case, I can write down an equation for the total population. And the total population size satisfies an equation which is extremely well studied in the literature. It's just a simple reaction diffusion equation. And work that goes back from 1975 to 1975 tells me there's a traveling wave solution to that equation for all speeds bigger than a critical speed. And somehow the stable speed is the critical speed, the slowest possible speed. And if b is less than or equal to 2 over 1 minus mu, so b was our cooperation parameter, then I have a pulled wave, and the wave speed, the critical wave speed is given by this expression, twice the square root of mr times 1 minus mu. If b is bigger, then I get a wave speed that depends on b in this way, and this is when I have a pushed wave. Okay, but there are traveling wave solutions for all those speeds. And what's really nice then is that I've also got a traveling wave solution for this system, because if u hat is the wave profile of a traveling wave that's traveling at speed c, then u hat of x minus ct gives me a solution for the total population size for my partial differential equation at the top, which is just a traveling wave front. And I know that these Poisson weights are conserved. And so I have a whole system which is a traveling wave, and the expression for the number of individuals at the point x at time t that carry exactly k mutations is given in this exact form. Okay, that's just a nice observation. Now, we can think of that population traveling wave as which I just wrote down. So this one here, as connecting at minus infinity the population in which, what's the right way to think about this? In which I've got a stable limit with k0 equals 0. So at minus infinity, I've got the population with u hat is equal to 1. And so my solution is just e to the minus theta is the k over k factorial. And it connects that stable solution to the whole system to the trivial stable solution at plus infinity, where the population is everywhere 0 and there's no individuals of any type. But I can also look at what happens when I try to connect solutions which differ by just one mutation. So if we were sitting in the front of a traveling wave and an additional mutation arose and it managed to take over, so I got a kind of click of my ratchet. So I had a population which in the wavefront, everybody carried at least one mutation, and in the bulk, there were individuals carrying no mutations. Then where those populations come together, I could think of an equation of this form, where the number of mutations, so here I've got everybody having at least one mutation. So that's meant to be what's happening in my wavefront. And behind that, I've got individuals which have no mutations and a Poisson profile. So that's what's happening behind the wavefront. And I could imagine that as time progresses, there might be some point x0 in the real line where behind the wavefront, I saw something that looked a little bit like the stationary distribution in which the fittest class has no mutations. And to the right of x0, at least far enough to the right of x0, individuals all carry at least one mutation, but it's still at stationarity. And I could ask, what happens if I solve my partial differential equation system, starting from that initial condition? What does it look like? How do the fitter types invade the less fit types? So individuals which carry no mutations are going to be able to invade the region where the ratchet is clicked because they're fitter. And that wave of expansion, which is happening somehow inside the wave of expansion of the whole population, is always going to be a pulled wave. And it turns out it's always got a speed proportional to the square root of s, therefore. And here's a numerics to show you how that works. So if I start a population from this sort of initial condition, then my population wave expands. And in the pushed case, this is the sort of picture that I will get. But if I look at the genetic wave where I'm sitting inside, where I've had a ratchet click and I'm asking, how can these fitter individuals, these yellow colored individuals, invade the region where the ratchet is clicked, then I have a pulled wave. And so I don't get invasion into the wavefront. It's still going to, spread out in this way showed in this bottom picture. So it's going to look like a right Fisher wave trying to invade the less fit types. Okay, so we've got two sorts of wave going on. We've got a wave at the population front of expansion. We've got this inner genetic wave, which is where after a ratchet click, we can expect that the fitter population coming from the bulk that's sitting a long way behind is going to invade the front. It's going to try and take over the front. And that's always going to be a pulled wave, so that's always going to happen. Okay. Well, that was what happened without noise. And of course, what we really care about is what happens with noise. So if I add noise, what I would expect, and I emphasize that we have not proved that this is the limit that we would get from rescaling our system of birth-death processes, but what we would expect, and for what there is overwhelming circumstantial evidence, is that our system of partial differential equations, which is this top line here, have an additional noise term, and the strength of the noise, which is really genetic drift, is going to be proportional to the population density that we've inserted. So just as when we looked at the difference between the Wright-Fisher model, the neutral Wright-Fisher model without space, where we had a square root of 1 over n u 1 minus u dw term, and then we added in something which told us what the deterministic influence of selection was on allele frequencies. So here we have the term we'd expect from a neutral Wright-Fisher model in space. So these W's are independent white noises, and the deterministic term, which tells us what the deterministic drift acting on these allele frequencies might be. Okay, so that's what we'd expect the system to look like. We have not analyzed this system. For anyone who's ever seen even one of these stochastic partial differential equations in one dimension will not think is very surprising. This is probably a very difficult system to analyze. And so what we've actually done is the royal we, what Felix has actually done is numerics for our individual based model. And what do we conclude? Well, what I want to show you is the accumulation of mutations in the wavefront. And when we talked about Muller's ratchet, we were able to talk about clicks of the ratchet where we lost the best class, and then every individual carried at least one mutation. But in this individual-based model, you can imagine that it might be that a deleterious mutation arrives in the wavefront, and then is very quickly overpowered by good mutations, or perhaps through chance, perhaps because they're fitter. And so what we see is an extremely noisy picture. And so what Felix did was he smoothed out that noise a bit to say, I'm only going to counterclick if it really, really shows. Okay. And so what do we mean by that? We're going to define T1. So T1 in our Muller's ratchet was the moment when we lost the best class. Now we're going to define loss of the best class in the front as being the first moment when individuals which carry one mutation get ahead of all the individuals that carry no mutations, and they get at least D deems ahead before they're caught up. So looking at the formula, though it's probably less informative than thinking about the sentence at the bottom, we write NK for the position of the rightmost individual that carries K mutations at time T. And then T1 is the first time that at some time bigger than T, the rightmost individual carrying one mutation is D deems ahead of the rightmost individual that carries no mutations. That's what this difference is, and that's bigger than D. And moreover, for all intermediate times, the rightmost individual carrying one mutation had managed to stay ahead. So it was always ahead of the rightmost individual carrying no mutations. And we're going to define that to be a click of the ratchet. And a bit of empirical work suggested setting D to be equal to 30, because then actually once you got ahead, you were likely to stay ahead for a good period of time. And then he measured clicks of the ratchet, where a click of the ratchet is this time T1. So that's the time when the ratchet clicks. And then the time when it clicks again is the time T2 with the analogous definition, but now it's individuals with two mutations getting ahead of the rightmost individual with one mutation and the rightmost individual with no mutations, and staying ahead of them and getting at least 30 deems ahead without being caught up. Okay. Now, to understand his results, to understand why it's quite difficult to understand his results, let's have another look at our original equation. So here's our deterministic equation with some noise. And what we wanted to understand was the impact of the Lie effect. And the Lie effect was being captured by this cooperation, B. But it's going to have two antagonistic effects here. One is that from a deterministic perspective, it increases cooperation, and so it increases the strength of the Lie effect. On the other hand, it also increases the genetic drift, so the term that's going on inside the noise. So it makes the noise stronger. So increasing the strength of the Lie effect will slow down the clicks of the ratchet, because the stuff from the bulk's going to just keep on catching up and outcompeting the stuff at the front. But it's increasing the strength of the drift will speed up the ratchet, because I'm just going to lose the best class by chance. So which prevails, as it turns out, depends on how big N is. So if I fix B and I change the population density, it's not surprising that as I increase the population density, so it reduces the strength of the genetic drift, the click rate decreases. So the bigger N is, the smaller the click rate is. So the longer I have to wait before I lose the best class in the front. But I will lose the best class in the front. For small n, genetic drift just wins. So for small population size, gene flow is just not very good at restoring genetic diversity in the front. So small n is this end of the picture. Big values of B are the darker plots, small values are the smaller plots. And we see that it's just the case that the as n gets smaller, the mean time to the first click gets smaller. The genetic drift prevails. For large n, gene flow prevails. So we see that the a pushed wave, if the population size is big, the effect of the gene flow is going to prevail, and it makes the time I have to wait for the first click longer. Okay, so that's why my picture flips over from having the darker color at the bottom when population size is smaller, and so increasing the drift is decreasing the time to the first click, or the position of the first click. They're equivalent, as you can see. But at the top, increasing B I'm increasing the strength of the Allee effect, and that's winning out. That's making the population wait longer before I lose the best class. N has more impact on the time for the first click for pushed waves than it does for pulled waves. There's almost no, so you're seeing that the difference between small and large N for a pulled wave, which is the yellow one, is very small. Whereas for a pushed wave, the difference in the time I wait for a click is very big. So the conclusion is that actually the Allee effect is very significant in the expansion load that we expect to see. And here, this picture takes a while to get your head around, but it's worth it. So this is, let's see, on the left, this is the color coding. So here's the legend, which tells you number of mutations. So yellow means individuals with no mutations, up to this dark blue color, which is individuals with 14 mutations. This middle panel is tracing at particular times. So time is going upwards. At each deemed position, what's the best class? So how many mutations are carried by individuals in the best class? Okay. So what we see is, of course, this gray is saying the wave hasn't got here yet. So this is the front of the wave. And we see that as the ratchet clicks, the best class in the front changes color. So that up here, we've got a lot of individuals in the front of the bad color. But this is only telling me the best class. And now we've got two snapshots of the population at particular times. So this is at time, on the bottom panel, is at time 400. This is what the wave looks like. It's reached deemed position around about 200. And the colors tell you the proportions of different types at different deemed positions. So you can map this yellow. Sorry, I should look on here. This yellow here, you can map over to yellow on the picture on the left, which says that up until deemed position round about 75, there are individuals that carry no mutations still. But to the right of that, we've had a click of the ratchet and then 2 clicks of the ratchet and so on. Okay, so you can see the clicks of the ratchet taking hold. Now, what are these stars? These stars are those inner waves. Remember, we showed what happened when you had pulled waves where the fitter class inside the wave was catching up with the less fit class. And this is coalescence of the boundaries between regions where individuals carry different number and different numbers of mutations, where the best class is fitter and less fit. So what had happened here is we'd had multiple clicks of the ratchet, and then we get 2, but each of them had just 1 mutation separating the fittest class. So this was 0 mutations, 1 mutation, 2 mutations, 3 mutations in the fittest class, and so on. And at this point, we see a coalescence so that the fitness difference between individuals to the left of that interface and the right of that interface is 2. And then we get another coalescence. So again, the fitter individuals are catching up in the bulk of the population. So we're seeing coalescences of these boundaries as the fitter individuals take over. The clicks of the ratchet are a transitory phase. On the other hand, this square, and it's a little bit hard to see, and if I'd been smarter, I'd have zoomed in and then put a picture of the zoom on my slide. It turns out this is an example where the fitness difference was big enough that it actually splits again. I see the ratchet clicking within that interface between the population here, which carries some number of mutations, and the population to the right, which carry that many plus 3. So it's the boundary between them splits again, and the individuals with just 1 mutation take over part of the wavefront, and then individuals with 2 mutations have carried on ahead of it. So we see an internal click of the ratchet. And what develops from this is a rather beautiful picture of branching and coalescing within the population wave. So when the population has expanded and we're seeing this expansion load left behind of individuals carrying deleterious mutations, the boundaries between the regions where the fittest individuals carry different numbers of deleterious mutations appear to form this rather elegant branching and coalescing system. And what we would love to do, of course, is understand that branching and coalescing system. Okay, well, that was one dimension. As I hope I impressed upon you last week, 2 dimensions is much more interesting typically. But in 2 dimensions, it's even noisier. And all we're going to do is show you a picture. So what Felix did this time was that he just took snapshots of the population. He just looked at the population at times 1, 2, 3, 4, and so on, up to 150. And what he did was he looked at the demes which were colonized, so the islands of population that were colonized in between times t and t+1. And he asked, well, when they were colonized, how many mutations did the colonizer have? So let's write that in symbols. So now I need 2 coefficients, I and j, to tell me which deme I'm looking at. But again, k is reserved for mutations. And we call the coalescence time. So what could happen again, because I'm in 2 dimensions, I've got a lot of genetic drift going on, is that I could have the population invading a new deme. So a population which was a deme which was previously empty, an individual arrives, but it might just instantly die again. And I don't want to fall for that. So I'm only going to look at demes which have individuals in them when I'm taking this snapshot of the population at these integer times and did not have individuals in them at the previous time. And I'm going to say at this time, which I'm calling a coalescence time, how many mutations are carried by the individuals in the fittest class. And that is the quantity that Felix has plotted. Now, these are not the same as the plots of the bacterial colonies that we saw last week. And in fact, what we would expect to see is some effect of selection really taking place within these. But what we are seeing is that the selection we've chosen is quite weak. And so actually, we're almost seeing sectoring. We're almost seeing colonizers with 0 mutations colonizing the next deme out. But what they're not successfully doing, what they ought to be able to do, is colonizing sideways. So these sector boundaries should move away from the yellow regions, which remember were the individuals carrying no mutations. And in all the pictures that I've got here, I've got 6 pictures. And what you can see is that that does happen here. And that's because going out along this kind of ray, this direction, there have been multiple clicks of the ratchet. And so the population, the fitness difference between individuals on the right and on the left of this boundary is really quite big. And I'm starting to see invasion. And this mirrors what you see when you look at bacterial colonies and you see fitter types invading. So I think it's safe to say we really don't understand anything about 2 dimensions, except that the pictures are intriguing. And we certainly don't have any way to analyze them numerically. But interesting things happen. And it is, I think, interesting to see that expansion load is a transitory phenomenon. Now, I just wanted to finish with an advertisement for Sarah's work. So it's 1 slide, I promise. And it's in some sense completely disconnected, but in some sense completely connected. So I haven't got much time to explain the connection, but the holy grail in all this would surely be to understand genealogies, to understand how individuals were related to one another. And we're not going to be able to do it in this situation where we have a ratchet if we can't even do it where we're just looking at a fitter genetic type expanding into a spatially homogeneous population. And that would be modeled by this Fisher-KPP equation with a white noise term. So last time we saw how to do this with the spatial Lambda-Fleming-Vio process. If you scale that appropriately, you recover this stochastic partial differential equation. Now, an enormous amount of work has gone into studying this stochastic PDE, especially over the last few years. And it turns out that genetic drift has a very, very strong effect on its behavior. So first of all, there is a traveling wave solution. It's got a nice stationary form, but that stochastic traveling wave actually travels much more slowly compared to the deterministic wave than you would expect. And it appears that the behavior of the wave is determined by rare events in which individuals get a long way ahead of other individuals of the same fitness, of the other fit individuals. So a particular fit individual gets a long way ahead of its close relatives, which are equally fit, and manages, while it's ahead, to produce an enormous number of offspring. And then the wave catches up and it's competing with people of equal fitness again, and everything starts to re-equilibrate, and it just continues almost like a deterministic wave. And then again, an individual gets ahead and I get a big burst of of population being produced. And backwards in time, what that corresponds to is that if I look on appropriate timescales, if I sample individuals from close to the wavefront, I'm going to see bursts of coalescence where lots of people are suddenly related to one another through one of these, because they all belong to a family that managed to get ahead. They're all descended from an individual that managed to get ahead of the wave. And the genealogy then looks like something called the Bolthausen-Schnittmann coalescence. Now, what Sarah has considered is a stochastic analog of that deterministic equation of Rock et al. That I showed you pictures of in the beginning, this pushed wave, in which we again add on a Fisher KPP term. So this is now looking to pushed wave invading space. And for those that care, this could be seen as a model of a hybrid zone. If we worked in higher dimensions anyway, this would be a model of a hybrid zone where we've got selection against heterozygosity. Homozygotes of type, let's say capital A, are fitter than homozygotes of type little a, and they're both fitter than heterozygotes. And then you get a traveling wave, but it's a pushed wave. And what Sarah has shown is that actually we can write down an individual-based model based on a Moran model, and the genealogy then is quite different. The genealogy then is a Kingman coalescent. So what we will see in data, what we will interpret when we look at data, which is determined by these genealogies, is completely different for a pushed wave to a pulled wave. And I encourage you to look at Sarah's work because it's always brilliant. And I'll stop there.
Great, thank you very much, Alison. So Ivan had to nip out early, so I'll take over the questions. If anyone, excuse me, if anyone has any questions, please unmute yourselves and ask as you will, and we'll see if we don't get into chaos.
Surely not chaos with you at the helm, Simon.
Well, I've been up too long today. And actually, I think, Sophie, can you, perhaps it's, I'll leave it. We'll leave it recording. That's okay.
Sorry, thank you for the talk. I was wondering why there is this scaling in the diffusion term. Is that a heuristic, or does it actually come from scaling the time?
This one here, it comes from not scaling.
Yes,
and in the previous ones, yeah. So every time I've put that 1 over n. So this was something we talked about in last week's lecture. I have not scaled, in order to arrive at this equation, I have not scaled the reproduction rates. So often when one writes down a diffusion equation, maybe it's clearest to go, there's a home button, there we go. It's probably clearest to think about the Wright-Fisher model. Normally in the Wright-Fisher model, what we say is, aha, well, our selection coefficient is small. And so I'm going to see changes in my population over units of n generations. So I'll measure time in units of n generations. And then I wouldn't get this n here, if that's showing up, just about showing up. But I would equally have to suppose that my s here was replaced by n times s. I'd have to scale time. But then I'd be measuring time in units of n generations. And what I did here was I didn't measure time in units of capital N generations as n went to infinity. I left things in real time. So I've moved it back into real time units. And in real time units, that just means that I would obtain this 1 over n here. Because if you scale a Brownian motion by 1 over n, it's equivalent to scaling the size of its fluctuations by 1 over square root of n. Does that make sense?
Oh, yes. Thanks very much.
Any more questions?
This is Leah. I have a quick question. Alison, is it easy to see how to go from the equation that involves the B for the Ali effect to the equation that has 1 minus rho? Because the one with the B seems like you have stable points, so that on one side you're pulled and on the other you're pushed. So does that translate easily to just adding the 1 minus rho term, or is that...
Yeah, there's a transformation, and it's even explicitly written out in this paper, which I did have on my desk earlier, so I wouldn't lose it, but I need hardly say I can't find it now. Yeah, you can just write down a transformation. In fact, in the introduction to Sarah's paper, which she was kind enough to put my name on, and it's on the archive from a month or two ago, it actually has that transformation written down. So it can be done. It's not completely obvious, but it's the same phenomenon.
Okay, thank you, Alison.
All parameter values. So, but yes, so you can transit from one to the other by making appropriate substitution.
Thank you.
Hi, Alison. This is Louis Fan.
Hi, Louis.
Hi. Can I ask, in your very last slide, for the SPD with this row,
yeah,
this validity effect, the noise term shouldn't it be also related with the row, or?
No, so that is because we've taken a different limit here. So this corresponds to a slightly different model in which you don't see that. So if we were modeling the total population size, but this is, we're assuming that population density is entirely constant, and we're just looking at the different genetic fitnesses. And it turns out that in that case, in this stochastic term, you won't see it. And I'm being a little, leaving this one over row E here. I have to choose the parameters a bit carefully. But I would, since I wasn't telling you there's probably a constant somewhere, but since I wasn't telling you how to derive this equation, I didn't feel too guilty writing down a schematic. But it's in the paper, Lewis. It's a good point. It's in the paper, and it comes out as a different order correction.
Okay, cool. Thank you.
Thanks. We've got time for a couple more if anyone's.
I have a naive question. It has to do with the distribution of the ages of the individuals in these populations, and how, I mean, the issues that I always have with traveling waves is that individuals live for a much longer time, so to speak. And so the fact that they're surviving actually contributes to how the genetic diversity is distributed in space.
I worry about that a lot, and actually that was why I devoted a little bit of time in lockdown to writing down a Wright Fisher model where that wasn't true. And it turns out that you get the same behavior, it's just that you think of an individual as being replaced by its offspring. So I can write these things down from a discrete generation model in which everyone lives the same amount of time.
Mm-hmm.
And you think of an individual as being replaced by its offspring if it only has one offspring and the offspring's the same type. And, okay. And it turns out that, yeah, I have worried about that a lot. And I think you're quite right to worry about it. And I should write it down carefully and properly somewhere sometime.
So if I could just add to that just really quickly, that would change though if we also had sexual reproduction in those zones, right? Because then that would kind of mix up the types.
Well, it turns out that it's okay if you're only following one locus.
Okay.
It gets nasty, I think, with two loci, and that's something I'm fretting over a little bit at the moment. Well, actually, I'm mostly fretting over keeping the department's buildings open, but I would be fretting over it if I were not head of department.
Okay.
Yeah, that's a very, very important question, I think. And I always think it's important to start with an individual-based model that makes some sense. And I agree that the Moran model, I did criticize the model that I presented here, the Moran model, because the 1 plus BU just looks like it's changing reproduction rates. And that's silly. But I then came up with a different one, and I agree with multiple loci, you've got to be really careful.
Thank you.
Okay, time for one more quick question. Okay, I think we've done for the day. First of all, Alison, many thanks. That was a great talk as usual. Secondly, I should remind everyone that the third of the series is next Friday. And the other thing to remind you is that the slides are on the IICD website and available to anyone who wants them.
Oh, so, and next week's talk is independent of this week and last week. It's a completely different model.
Great.
I also would like to remind everyone that you need to re-register for the third one. Every time you each talk, it's a separate registration.
Yep, that will be good. All right. Thank you very much, everyone. Have a good day and see you all later.